Hello everyone, this is Esfandiar Khaleghi. Welcome back to another session of the CAD CAE Bootcamp. In this session, what we're going to do, we're going to talk about the finite elements modeling and finite elements analysis, and we're going to put it to the practice using the Siemens NX and using the Siemens NX Nastran solver. So whenever we talk about the finite elements method or FEM, basically we talk about the numerical techniques that we will need to use in order to perform the finite elements analysis or FEA of any given physical phenomenon. Basically, I'm not going to go through the FEM today. We're gonna leave it for the time that you will have the actual session at university, which we'll talk about in different numerical techniques. But what we're gonna do, we're gonna use those as a solver, which are ready to go, and then practices using the Nastran solver, which is available using the Siemens NX. But of course, if you're interested to go to the mathematical things behind the scenes and in order to compare your result with a mathematical result, which you will be able to do it, I will recommend to study these at your own time. So hopefully by the end of today, we'll go through a basic introduction of the finite elements modeling and finite elements analysis, and we're going to go through the process of the design analysis using the finite elements modeling and analysis as well, and we will put it to the practice using the Siemens NX and particularly, as I mentioned earlier, using the Siemens NX Nastran solver. For today, we will have a brief introduction about the finite elements modeling and analysis, and I'll talk about the different design processes, what is actually FEA, and then what's the processes the FEA has, and we're going to go through a couple of the wrong FEA examples, and we will have the 3 different tutorials which we will experience the different FEA levels with the different meshes using the 0D, 1D, and 3D meshes. Hopefully by the end of today you will have a good understanding of at least a basic of the design analysis and the necessary logical steps you need to take for the design analysis and simulations, and hopefully you will be able to perform the pre-processing, or we call it the finite elements modeling, the processing, the solution side, as well as the post-processing when you see the results of the FEA. Product design is a highly complex process with the multiple objectives, requirements, and constraints, which all of them need to be satisfied for the final product to be successful, to have a successful product. The important factors that the designer needs to keep in mind, include the aesthetic, for instance, the functionality, the cost efficiency, the durability, and safety, of course. While the aesthetic appeal of a product is not quantifiable, the other design aspects are, and they can be accurately tested. In the traditional design, as you can see here, the initial design is derived from the practices and the past experiences, for instance, which of course limit the creativity and leaves the little room for the radical innovations. Come up with a truly new or groundbreaking design without relying on the best practices, they become risky and can lead to poor performance. So the only way to ensure the durability of such a product is to perform a high number of design iterations until the criteria are met. As you can see here, so whenever they come with a design, they of course start to design it using the computer-aided design software and then put it to actual practice. But in order to do that, they have to make a physical prototype and then put it to the testing, and then if they are not happy with it, of course they have to go back, redesign it, make another physical prototype, and then put it to the actual testing. So traditionally that means a high number of physical prototypes to be made, which are time consuming, and of course they are expensive testing phase. So as I mentioned, these process is costly, time consuming design cycles that they have to go through, and usually it was one of those things that actually limit the companies to come up with the innovative or completely new and groundbreaking designs. And of course the physical testings cannot and of course should not be eliminated from the product design process entirely, but on the other side, multiple product building cycles, which account for the bulk of the financial and time costs, can be easily avoided by integrating the visual simulations into the workflow. With the CAE or computer-aided engineering, you still have an iterative design process, but the days, weeks, or months of making those kind of physical prototyping and testing, they are replaced with the hours or sometimes even the minutes of the simulation to run. So what you will be able to do, you will be able to put it to the virtual testing using the FEA or CAE, and then come back to your design, update your design, and redesign it, and start making the actual prototype when you're almost sure about what kind of result you get, and that's for just a reassuring to make sure that everything works fine. And this is the beauty of the CAE, using the computer-aided engineering, which you can use it either on the FEA side or you can do it on the kind of CFD part of it. But let's talk about the FEA and Finite Elements Analysis, and to find actually what it is. What is FEA? The Finite Elements Analysis is an engineering computational analysis method that will help us to determine the strengths of the product in response to the loading, for instance, which might be explained in the operating environment that we designed the part for. And whenever we talk about the product, it can be within the part level and assembly level, and of course both of them, which is really important. FEA simulates the behavior of the real component, and as I mentioned, can be an assembly as well, with an idealized mathematical model, which we call it the finite elements model, including the physical condition which is going to operate on that environment. So model then will be analyzed by the finite elements analysis solver, which then will calculate the results data that reflect the design behavior to the applied boundary condition. So what we're actually aiming to do within the FEA, we're gonna apply a few finite elements model mathematical expression on the actual model that we have to predict what kind of response the product will have in its operating environment. Whether design gonna fail and wouldn't be able to fulfill what it's looking for. For instance, whenever we design a bridge, whether it would start to buckle or whether it start to crash and collapse, or whenever I design a car, what's going on whenever it's going to happen when there is a crash going on. So we will be able to actually apply these mathematical expression to predict what the model gonna perform in those cases. So in order to do that, in order to apply those kind of mathematical expressions to it, we need to start breaking the model into the smaller pieces, which we call it the discretization of it. So in order to be able to discretize and make it to the smaller pieces, we need to apply meshes. And that's why whenever we talk about the FEA, we always say that we have to apply it within the part level and assembly level, and there are two different analyses we have to do on it. The reason for it, because once we apply these kind of discretization and make it to the smaller pieces and study every single forces of those, once we are doing it part level and once we put it into on top of the other part and make it the assembly at the end, those forces or those changes in a shape might have an impact on the other part as well, which is why it's really important actually we do it onto the assembly level as well. What we mean actually by the mesh generation, why we actually do that. So let's say we're gonna study these parts and see the amount of displacement we'll get because of the force that we have. So we'll have, of course, this stiffness, which we need to multiply by the displacement in order to get the force. Or in this case, we already know the force. We know the stiffness, which comes from the properties of material. We want to see how much displacement it will have, which seems to be quite straightforward because it's a normal square. It's a normal shape. It's an easy thing to do. However, whenever we have the complex geometry, then what you need to do? In order to find out the displacement in this model, it's not something easy to do. That's why what you need to do, you need to break it down to the smaller pieces to be able to still apply the same sort of formula that we have. And in order to do that, there are different methods that you would be able to generate your mesh. Whether you're gonna go with the hexahedral, tetrahedral, pyramid, which basically just the shape of those kind of smaller pieces would change, as you can see here, and then you would be able to apply those formulas if in case you're going to do it through the hand calculation. Of course, through the solver, we're going to use the solver in order to do those kind of finite elements methods for us, and that's why we're going to apply for the mesh. But then the other side of it brings to the discussion that what kind of mesh size you're gonna go for. So whenever we talk about the mesh and discretization of the model to the smaller pieces, how many pieces you're gonna get out of it? So for instance, you wanna make these hook to the 1,000 pieces, but why not about it to the million pieces? And that's why you need to decide to find the appropriate mesh size. If you increase the size of the mesh, which you will then end up by having the big mesh elements and to the smaller piece that actually you divided your model to the smaller pieces, you might not come with the accurate results. But of course, if you decrease the size of mesh and then increase the quality of the mesh on the other side, you need much more computer power. For instance, if you want to analyze this model with these kind of mesh elements, might take, I don't know, let's say 5 minutes. This one would take an hour. And then, for instance, if you're talking with the bigger scale, let's say, I don't know, the Airbus wing, for instance, it might take few days or few weeks of the analysis. So what's the aim you're looking for? You're looking for to play with the size of the mesh up to the time which you come up with some sort of independency, which means that from now on, whenever you change the size of the mesh, the result you get is not that much different. And that's the goal of the mesh size that you're looking for. Of course, there are lots of methods that once we go through the FEA using the Siemens NX, we talk about it, such as the local meshing, different type of the meshing, and these sort of things which are really important. Otherwise, the result you will get is not that accurate. So whenever we talk about the FEA analysis, we talk about these kind of 3 processes, which is really important that we need to follow. So we'll start by the pre-processing, which basically what we need to do in this stage, we need to define the problem we have. So in order to do that, we need to have a geometry. So of course, we need to have a computer-aided design model. And then you need to find out the material is going to be used, because each of them, they will have different properties, which we need to work with it. We need to find out what's the loads we have, how much they are, and also the boundary condition, the condition of the part we have. Then we need to talk about the mesh generation and how we're going to discretize it, which we need to talk about the nodes, the elements generations, the type of the mesh, whether it's a 0D, 1D, 2D, and 3D meshes, the element shapes as well. And then once we define everything into the pre-processing, we take it to the next stage, which is the solution stage of it. Within the solution stage, we'll start by doing the different analyses of the structural analysis, for instance, fatigue, thermal, vibration, and buckling, and so on. And what we will do based on those kind of physics and assumption that we have, we generate the FE equation and the matrices. And then we do the linear and non-linear analyses, and of course we do the processing on that side. Once we analyze it, then we'll get the results, which the results are important. We want to see what we're going to do with those results. Whether you're going to make the plot, for instance, whether you want to generate the graph, because basically these results you want to use it to, of course, come back and redesign your part if it's necessary, or if you're happy with everything, to analyze it and make sure that your design is fine and can survive in the condition that actually you as a designer designed the part for. And of course, you would be able to start to make a kind of sub-modeling and study the other part of the part that you have as well. These 3 stages is almost similar among any other software. It doesn't matter what software you're going to use. Always for the FEA analysis, you do these kind of 3 different stages. And probably one that you are familiar with the coding, they heard about the GIGO, which basically means the garbage in, garbage out. So whenever you work with any software, you're dealing with the garbage in, garbage out model, which basically says that whenever you have a garbage data, you have a perfect model, the result you get is garbage. Or whenever you have a perfect data, but the garbage model you have, then you will end up by garbage result. And the same sort of thing apply for the FEA, and that caused for the wrong FEA, which is quite common. So you might have a fantastic model, everything is designed properly, but then once you're gonna implement those kind of loads, those kind of conditions, either you don't do it properly, either you don't make a proper FEA analysis on it, or either you don't predict all the forces or all those things within that environment which impact your design. The result you get is wrong. which is really important, because what it actually happened, you release the part and then the part fail, and sometimes those fails will have some kind of fatalities because the product deal with the human body, and that's really important. But the other hand, you might have a perfect condition. You consider every single elements of it. You consider the forces, you consider all the conditions, but then you don't design your part properly, and instead the result you get, they are wrong. That will end up with lots of the wrong FEAs. That's really important to consider. So whenever we talk about the FEAs, as I mentioned, so it's really important to consider that how much damage you will end up doing while you do a bad FEA. Of course, these are unintentionally again, but this is really important. So you can see, if you search for the bad FEAs, you can find plenty of them. For instance, you can see that the bridge has been buckled out, and in Taiwan that it collapsed. Then you can see, for instance, the jack-up rig sinks in Saudi Arabia due to the wrong FEA. But something usually I played a video for, I'm gonna put the link so you can watch it at your own time. It's the Deepwater Horizon, which you can see in the videos. The Deepwater Horizon drilling rig exploded in April 2010, which due to something that they didn't, some condition didn't consider in their FEA, that at the end the BP it cost around $65 billion for the BP due to the damage they've done. They had to pay 1.7 billion as a charge. So you can see that they consider every single things, but then within the assembly level, they almost forgot one condition, that this is what happened. So FE is really important, and it's one of those kind of really well-paid jobs, to be honest. Whenever we talk about the FEA, we are dealing that usually as a CAD designer, for instance, you are dealing with some sort of 25,000-30,000. But once you talk about the FEA and become the expert into the CAE, your salary would then increase to the 35 to 50,000 pounds. So it's a really good jump, but make sure actually you have to know these things and consider every aspects of that. It's a really good and well-paid job, but again, lots of the aspects of it that you need to consider. So what we're going to do now, we're going to go and do a simple FEA model within the Siemens NX, which basically with that one, we're going to go through 3 different stages: the pre-processing, the solution part, and the post-processing. And you can see once you learn this one, is almost the same sort of thing within any other CAE software. So it's really useful to go through it. We're going to start with that one, and then we're going to have the few other tutorials, which we're going to go to the much more depth of the FEA analysis. So now let's have a look to see how we'll be able to open up the finite element modeling and analysis side of the Siemens NX. In order to do that, what I'm gonna do, I'm gonna open up a new file first, and let me go and open up the bar file. But again, like the assembly that I talked about, let's create a new folder and leave it there, because really important. I'm going to show you that once you're going to continue, you see that the Siemens NX is going to create a few new files for us. I'm going to call it the FEA tutorial 1. And what I will do, I will copy this file and leave it in here and open it there. So you can see I only have one file, which is a bar.prt. It's a normal bar that has been extruded. And in order to open up the finite elements modeling or CAE part of the software, there are different ways in order to do that. Whether you want to create a new file, which you can go to the file, click new, or you can go to the file and click new in here, or you can come here and click new. And what you need to do, you need to move on from the model, which is usually by default, go to the simulation. And first you need to create one finite elements modeling, which you can see in here, and one simulation side. But what I'm gonna do, I'm gonna tell you something which is quite better and simpler in order to do that. It's while you're in open up the file, you're gonna go to the application and click on the pre and post, which by clicking on that, you would be able to create the new FEM and FEA files all together. You can either, I'm going to repeat again, go from the home to the application, open up the pre and post, or you can go to the file and then click on the pre and post. So once you click there, you see on top you will have the few options. So you see that you will be able to create a new FEM and simulation file altogether. By clicking there, you can see that you will be able to create a FEM, finance analysis modeling and simulation altogether, or you want, if in case you want to only make the one final elements model, you can create there as well. You will be able to make, for instance, if you have an assembly, to bring only one part of it and make a linkage with them within the wave. If in case you have a fully symmetrical model, in order to save the computer power, you will be able to split it into the two pieces and analyze one part, and let the software to copy the rest of analysis on the other part, which will have a tutorial on that as well, and so on. For this one, it's quite simple. What I'm gonna do, I'm gonna go and create a new FEM and simulation. So if you remember what we've done, we went to the pre-post, and now we're gonna click on the new FEM and simulation. Right now, you will see that once I click on there, the software is going to create two new files for me. One is by the .FEM, which stands for Finite Elements Modeling, and one is .SIM, that's for the simulation, the Finite Elements Analysis simulation. Because I already opened up the file, I don't need to bring it here, but if in case it's a new file, yeah, this part of it would be enabled, and I can click on open to open the part. In this case, I already have the file. If in case you have the few one, you will be able to just click on the one that you're looking for. So if in case you have the 10 files open, you would be able to pick up which one you're looking for. And then depends on whether you have a fully assembly. Let's say I open up the fully assembled and you want to only study one part of it, you would be able to come here and change it to select and select the body that you want to work with. In this case, I only have one. So what I'm gonna do, I'm gonna change it to the all visible, because I only have one single body to use. But again, as I mentioned, if in case you have the assembly, there are a few of them open, you can pick up which one you're gonna go for. Also, you would be able to control the quality of it, the polygon body resolution, which basically control the quality of the CAD once it comes to the finite elements modeling and analysis. Whether you want to have it on the high, of course, it takes much more time to doing the simulation. Usually, we're gonna go for the standard unless you have a really complex geometry with the high precision, and that if in case, for instance, if it's a bigger scale, because it takes time, then you will decide on the quality of it. Basically, this quality will then change the quality of your mesh. Again, it's really simple geometry, and usually we keep it on a standard unless you have a really complex body with even a bigger scale. Also, into the geometry, we will be able to simplify the model. So one of the reasons you might be able to simplify your model, for instance, if you have a bar, you want to compare your hand calculation with the one in here. So what you will do, you want to only study it as a line, so you would be able to come here and tick the lines, for instance, in here. In this case, I want everything, so I don't want to simplify the model. It's a simple model, to be honest. I don't need to make it much more simplified than what it is. But again, for instance, if I only pick up the lines, it only pick up the lines in here. And this is how we use these basics. I'm gonna cancel it because I don't want to pick any one. I'm gonna bring the full model. But if in case it's just a line, you would be able to go to the geometry option and tell the software I want you to only import the lines. Again, for the solver, you would be able, that's the beauty of the Siemens NX, you would be able to use the different solvers. The different solvers would have the different kind of calculation behind the scene. Even the beauty of it, it has different solver from other softwares. The ANSYS, Abacus, sometimes you want to go and do a statistical analysis. Abacus is really good at it, you might use that one. Or if in case it's a car related, Esfandiar, you are really good in the analyzing the car crashes, you would be able to do that. If in case you want to study the, for instance, thermal flow, and these sort of things, you would be able to pick it up in here. This time is a normal statistical analysis. My model is static, so I'm gonna go with the Siemens SimCenter Nastran, which is really good. It's quite powerful, and most of the analysis we're gonna go for the Nastran solver. Again, as I mentioned, I can pick up also what kind of analysis I'm gonna have, whether it's this structural analysis, whether it's the thermal analysis, and so on. In this case, it's structural analysis. I'm gonna pick up the structural analysis, and I'm gonna leave everything as default. So in this case, I haven't changed anything. everything is the bodies is by default, even solver default. I haven't changed anything. I'm gonna click on OK. So once you click on OK, what it does, it's trying to create the 2 new files for you, and also now it asks you to give information on this on the solver, on the solution part of it. You can rename it, put it to whatever solution you want to pick. You can right now even change the solver name. I'm gonna keep it as a Nastran because it's the best one in what kind of study we're gonna do right now. It says structural analysis. Also in here is solution type. I'm gonna keep it as a SOL 101, the linear statics in here, because my model doesn't have an acceleration, doesn't move. That's what I'm gonna go with there. But if in case I'm gonna go and study the linear buckling, I would be able to go and study and change the solution type there. In this case, I'm gonna keep everything default, and I'm gonna click on OK. So once I click OK, now I come to the Finite Element Modeling and Analysis environment. So you can see on the right, on the left hand side, you see the simulation navigation on the top, which you will have the information on your simulations. If I go next, you will see the results there. Of course, right now I don't have any results, so it's not something available there to watch. Something else I wanted to mention, usually simulation file view is off. In order to switch it on and see it back, you would be able to see them there. Any of the models that you're working, if in case you're open, you will see them there. Let me close these. If in case you want to close any of these analysis for before, you would be able to go there, right click, and then click on close, and it will close it down for you. And let me close this one down as well. And this is the one that I have. So you will see it has the 4 different layers. So usually you might see it like that. Make sure you click on plus, you see 4 different layers. The first one is actually the part level that I have. The next one is a linkage between the part and the mesh that I have. Is basically the Finite Element Modeling and Analysis connection that I have in here. And this is what I'm interested in, the mesh level. And also once I click to this one is basically my finite elements and simulation side of it. So let's start with the mesh. The reason I'm going to start with the mesh, because I want to discretize my model to make it to the smaller pieces. So as a review, what we've done so far, we open up the file, bring it out to the pre and post, and now we're going to apply the mesh. So once you click on the mesh, you can see these bar on the top will then change. You can see, for instance, if I go to the simulation, this is like that. And once I click on the mesh, it will then change to the mesh. I have the different type of the mesh that I would be able to use. So I can go with the, if I click on more, you can see I can go with the 1D and 0D mesh, if in case you want to only analyze a line, for instance. 2D mesh usually whenever you study a kind of plane surface, something like that, and 3D mesh for the 3D models. There are the various type of the 3D mesh you would be able to use. Usually we will decide between tetrahedral and hexahedral. Hexahedral, the Siemens NX call it the 3D swap mesh. There are lots of papers you can read at your own time about the difference between those. Usually hexahedral we go with the kind of the simplified models, because what we are aiming to do whenever we make it to the smaller piece, discretize the model, we want to make sure there is no torsion between the elements. Tetrahedral has been used quite for the more complex. It's one of the best ones, to be honest. Well, of course, needs much more computer power in order to generate it and do an analysis. But of course, if you have a simple model, you can go with the hexahedral. And you can see here, it's between 8 to 20 nodes elements, whereas tetrahedral is between 4 and 10 nodes. I'm going to go with a 3D tetrahedral, which is quite common for the 3D models. And what I need to do, I need to pick up the body I want to apply the mesh to. In this case, it's this one. And you can see I have the different type of it. I have the C tetra with 4 nodes and 10 nodes. You have the different kind of type as well in here, again between 4 nodes and 10 nodes. The only difference you can see is just the shape of them will then change. I'm gonna go with the C tetra 10 because I want to increase the number of nodes in here. And now I need to put the element size. So element size is really important. If you remember within the lecture, I mentioned that it will impact the quality of the mesh. Once you increase the size of the elements, then basically the number of elements will then decrease, the quality will drop. If you increase the if you decrease the element size, let's say for instance, if you decrease that one to 1, then because the size is limited, is make it smaller, then the number of elements will then increase, then you will have the higher quality. I'm going to show you an example here. Let's put it as a 30 and let the software then says. I'm going to click on OK, and you can see now the software is down, give me an error and tells me, are you sure? Because of the size of the elements that you put as a 30 millimeter, you might not have a good mesh and you might not have a good accuracy. I'm gonna click on yes, because I want to tell you something. Now if I go to the 3D collectors, because that's a 3D mesh, if I click on plus, and that's a solid model, I'm gonna click on plus, you see that's my mesh. If I then move this bar and then change this one, and you can see I have 2288 elements in total. Now what I'm gonna do, I'm gonna double click in here and then change, so for instance what it does in here, because I click on the yes, it went and automatically pick up the one that it thinks is suitable for me. But what I'm gonna do, I'm gonna then now force the machine to go with the 30 elements that I wanted to go. This is what the computer recommends, 2288. I'm gonna click on it, okay, and I'll say no, I don't want to have a better size. I'm gonna have a full control, and you can see if I go with it with the element size that I put here, I only end up by 222 elements. That's why I wouldn't have an accurate result. So what you would be able to do in order to prevent that one, you can either click on the yes and let the software to do, or what you can do, you can come here, click on edit, and there is that option here, which is the automatic element size. If I click on that, then its software tells me 7.98 is the best one. And if I click OK, and you can see I will go back to the same sort of the elements counts. But what I'm gonna do, I think even 7 is a little bit too much. I'm gonna come back and then change it to the 5 and click on OK, and you can see that the number of elements and actually double it up, and I think that's the best one based on these. These again needs an experience. You might need to play with the size of the mesh to find out the best one based on the model. And what you usually do, you change the mesh size, do an analysis on it, and then get the result, and again compare it with another mesh size to see which one is much more accurate. Let me go back to that menu and tell you the other thing. So if you remember, we pick up the body, we decide what kind of type of the elements property we're going to go for. We apply the elements size that you are looking for as well. Also, the other thing in here, you would be able to have a control on the mesh, especially on this, for instance, whenever you have a curvature area, as well as the internal mesh which you have. If you search that one on the Siemens NX, I'm gonna bring it here. This is what it says. So for instance, if you change the slider for the curvature based variation of that size to the 0, then you will have basically software use the overall elements length. It doesn't change anything, doesn't apply any kind of local meshing for that curvature. However, if you then bring that closer to the 50%, then the elements around those areas would then increase between 60 and 100% of overall size, and that's why you will have much more accurate results. And again, you can put it on 100% that you will have the elements and the sizes of those elements between 10% and 100%. And you can see this is what it happens. Basically, once you go to the 100%, you will have much more the accuracy on this side of it. That's the A1, that's the B1, and the C1. This is when you apply the kind of local meshing where you have there, which is really useful, and it actually changed the quality of your mesh a lot. The same sort of things also apply in here. If I then, for instance, change the internal mesh gradation, is the same sort of thing. So usually by default is like that. This one keep it as a 50% because it wants to increase the size of the mesh there. Basically make the mesh sizes in half. So then you will have much more mesh whenever you have a curvature area. And so let me click on OK. I don't want to change anything else in here. And now we've done everything with the mesh. something is really important. I need to define my material as well, because each material has a different properties, and I need to specify the material. Otherwise, once I'm gonna run the solver now would then show an error that I haven't defined my material. So in order to do that, what you can do, you can go to this one, to this level. This is the mesh level, a little bit higher level, the group of them. Right click on it, click on edit, and then click on this icon, and you will see here that option for the material. What I'm gonna do, I'm gonna go to material and pick up the material I'm looking for. Let's say go with a steel in this case, and also make sure it's isotropic, so changes it would be in all directions. Same thing. I'm gonna click on OK, and I'm gonna click on OK. So what I've done, I've applied the mesh. I've also defined the material. So what I'm gonna do now, I'm gonna go to the simulation level. I'm gonna go one up from this mesh level to the simulation level. And what I'm gonna do, then I'm gonna decide what kind of constraint I'm gonna use, where I want to fix my model. Depends on what kind of condition I want to make in here, I will go to the different kind of these things in here, which will have the different tutorial for some of them to understand these better. In my case, I'm gonna go with a fixed constraint, because what I'm gonna do, I'm gonna fix every single element of that hole. So none of those elements would then change. What I'm gonna do, make sure the inner part of these holes are gonna pick it up. I'm gonna click on OK, and you can see that kind of fixture representation the sub will show to make sure this part is fixed. What I'm gonna do now, I'm gonna insert the force on that area. So now once you are happy with whatever type of constraint or how many type of constraint you have, then you go to the loads. Again, depends on what kind of a study, what kind of forces you have, whether it's a temperature, acceleration, force, bearing, torque, and so on, or a pressure, you would be able to pick them up in here. In this case, it's a normal force. I'm gonna click on the force, and I'm gonna make sure it's not the edge, it's the inner part of this hole again, and I'm gonna put, let's say, put 2000 Newton, for instance. What I need to do, I need to also specify the vector. I'm gonna pick up that vector, and I'm gonna reverse it back, because I'm gonna have the force in this direction. I'm gonna click OK, and you can see I have the force in on that direction. So what I've done so far, I discretized my model, I applied the mesh, then I applied the material, put the constraint, and now put the load. Everything is fine. Now I'm gonna let the solver to solve it. So let's double check few things. You can see once I'm to the FEA level, I have the fixtures here to the constraint. If I open it up here, I have the force in here. Something is really important. This is the solution one, if you remember, that I created. The constraint, now they are active. They are here as well. Also the loads, they are there and active. Because sometimes you might do changes and these become inactive. So it's really important, make sure they are active. If in case they are not active, what you can do, you can right click and click on add to active solution, if in case they are not active in here. So now what I'm gonna do, I'm gonna let the solver solve it. So make sure into this level, finite elements modeling level, and what I'm gonna do, I'm gonna go there and click on the solve, and what I'm gonna do, I'm gonna click on OK. So what it's trying to do is trying to open up the Nastran. If in case you're doing it for the first time, you might see it MS dot's gonna open up for a few seconds and close down. That's why, because it's gonna take you to the Nastran and apply the formulation there. I'm happy with everything, so I'm gonna click on yes in here. Even in here, you would be able to check the how the convergence you had with the Siemens Nastran that actually tried to solve it, and the model has been converged. And this is the number of kind of equation it applied to these kind of elements in there. I'm gonna dismiss this one. Job is done. Make sure this one is down. Now I can close this one down. And you can see the job is completed. Make sure you close it once the job is completed. If in case it's in progress, you shouldn't cancel it, because you wouldn't get any result. I'm gonna cancel this one because the job is complete. I'm gonna close this one down as well. And if I go to the results here, if I click on plus, you can see there's a structural, because that's a structural result. If you remember into the solver, we wanted to have a structural analysis, and now it's colorful, which means that the result has been loaded. So I'm gonna double click on this one. which basically take me out from the simulation navigator to the post-processing navigator. It's a solution 1 because I name it as a solution 1. You can rename it to whatever you're looking for. If I click on the plus, you see a different analysis. I would be able to go and check the displacement nodal, which basically the displacement for every single node. Every single of those nodes, they connect and form an element basically. Every single of those dots will form the different elements. I can go and study the rotational, the stress elemental, the stress nodal. The difference between those is a stress for every single element in there. Every single element, let me pick it up. Every single of these. Or I can go and do an average between every single node and element. You can see these are nodes that, for instance, these nodes, the 3 nodes, would then form one element. That's the difference between them. And of course, I can do the reaction, force and reaction moments. Let me go and then check the displacement. I'm going to click on plus. I'm going to go and see the displacement in X direction. Or I'm going to go and check the displacement in magnitude of it. And you can see I have much more displacement there, of course, because I fixed the model there and I insert the force there. Of course, that I will have the displacement there, which is 1.6 millimeter displacement that I have there. Let's go and check the stress, for instance. Again, you can study in the different planes, for instance, or you can go with the one Mises, which basically the average of it again. And you can see because the model is trying to bend, then you have much more stress in that side. That's for the elements. Or I can go with the average between the elements and node, which is this one, and you can see that's the stress that I will get. It's a 531 megapascal stress that I have on there. So that is how you would be able to analyze the basically the results. So let's go and talk about these. So with these results, once you get it, you would be able to, for instance, if I come here, I can go and apply the banded display. What it does with the banded display, it gives me the banded. So that's really good for me to understand the different changes in the stress. Or again, if I want, for instance, I can do the same things for the displacements. That you can see, you will have the band, the areas that you will have much more, for instance, displacement in here, for instance, or the same things for the stress. Let me switch off the banded one, and what I'm gonna do, I'm gonna go here, and by default is on contour, and I gotta change that one to the ISO line, which basically with ISO line I would be able to see the planes that I will have the changes there. I can go and then make to actually see the plane. So that's really good way to understand whenever you actually those kind of changes, in this case for instance the displacement would happen. So I would be able to analyze it better. So for example, if my model is failing there, I would be able to come back and redesign that part of it as well. And I can see them as a cube, for instance. I can see it as a sphere. So these are basically for different analysis. They might be useful for you. I'm gonna bring it back to the contour. I'm gonna look at it like that. What else? Let me go and, for instance, this one you can see with the meshes. If I click on there, I would then get rid of the meshes, so you won't be able to see it. I'm gonna bring it back, so that would be able to see the meshes. What else? If in case I want to exactly read the amount of the information on one specific area, I can go to the identify results, and let's say I'm gonna see the, for instance, the displacement in there. I can click there and I can see the displacement, and then for instance compare with the displacement that I have. There is almost nothing displacement that I have, so you would be able to specify the points and it would then displace that information there. Also, what you would be able to do in here, you would be able to, for instance, then the layout of it is by default is single view. I can split it and put it to the different views. Let's say I'm gonna put it, for instance, on let's say the 4 views, and within 4 views then I can have a full control of it. For instance, this one is, let's give it as the magnitude in here. I'm gonna go and then pick up this one and then go there and apply the one Mises there. So what I'm gonna do, I'm gonna bring that one with the one Mises, right click to it, and I'm gonna click on the new plot, and within new plot I would be able to pick up where I want to have it. Let's click on there. Let's the first one I'm gonna leave it as this one. So the first one is the displacement, the second one is the stress. Let me go and for instance get the graph. So what I'm gonna do, I'm gonna make another displacement. Let's call it the magnitude. I'm gonna click and to get the new plot. I'm gonna pick up this one, and let's do the same things for this one as well. I'm gonna right click on one misses, new plot, and I'm gonna click there. So what I'm gonna do, I'm gonna go and on this one, that I just created for the stress, I'm gonna go and click on the create graph. For create graph, what I'm trying to do, I'm trying to see, for instance, the difference between the stresses. Depends on what you want to get from the stress. Let's say I'm gonna then get the change between the amount of stress between these points. You can pick up whatever points you want to go for. I'm gonna go with the one that I will have the change, and I'm gonna click on OK. Now it asks me where I want to save it. I'm gonna leave it there. And you can see that's the graph that I will get from the changes for the stress. Let me do the same thing in here. Let me, for instance, go for this one. Make sure that it applied to this one. Okay, I'm gonna zoom out. I'm gonna get the graph as well. This time is for the displacement. Let's get the displacement in here. I'm gonna start from, for instance, this area. I'm gonna go with that area, that area, that area. I'm gonna go for that curve to see what sort of displacement would then change. I'm gonna click on OK, apply there, and you can see, of course, that's the displacement I have. So this is how you will be able to have a full control. That's really good and useful way basically to present it. Let me also tell you how you can, for instance, animate something. Let me go back to, for instance, this one that I have the magnitude. Make sure this is applied correctly in here, and I'm gonna click on animate. And if I play there, you can see that this is the animation of it as well. I would be able to control the frames per second to make it slower and faster, which is really good, especially for the presentation. It just tells that what sort of displacement you have on that specific area. Also, what you would be able to do once you finish it, let me click on stop. If in case you want to generate the report, so the report will have all this information, what you will be able to do in here, you can go to the home tab, and next to the solver you can see this option which says create report. If you click on there, you can pick up the template. So these are different templates that you have, and you would be able to pick up the one you're looking for and click OK. I don't know whether it's JavaScript installed properly or not. In this case, not. Whenever this is really important because the JavaScript is not installed properly. That's why I get this error. But I'm gonna show you if in case the Java was installed properly, what kind of reports you will get. Let me show you to you in a second what sort of reports you will get. This is one report that I found for you. For instance, if I open this one up, you can have a look. That actually gives all the information: what kind of constraint you applied, what's the material you define, what kind of loads did you apply. So it has all those information, as well as the for instance, how these has been applied, the direction of them, the result. So it's a really useful tool. I need to chase it up to understand how we can ask the IT to install it. But basically, if in case you're using the Siemens NX on your own machine, you would be able to see that to generate the report, which is a really useful tool to have and to include in your product design document. The other thing which I wanted to tell you before I finish this part of the tutorial, if you go to the file that you remember, if you remember that I created a new folder in here and I saved it into one folder. So now if I open this one up, you can see this is the file that I have and the rest. So that's why I ask you to put it and save it to the one different file. So what I'm gonna do, I'm gonna go back to the model that I have. Let me go to the windows of this one. And if you're happy, for instance, with everything, what I'm gonna do, I'm gonna click on the save, for instance, do a Control and S and save it. And now if I go there, you can see that's the main file that I have. That's the finite elements modeling one, that's the simulation file, and the rest. So that's why I ask you to put in one actual folder, and make sure you don't remove any of these, because if in case you remove these, once you're gonna reopen it up again, you won't have access to the file. But now what I can do, because I already saved everything, what I can do, I can easily go back, for instance, in here, go back to my model, and let's say I'm gonna go, for instance, to the load, right click there, and then change the force, for instance, to something else, and then run and solve my model one more time. So it's really important is how you save it properly and put it on your actual model. So what we're going to do, we're going to continue with a couple of more tutorials with different meshes and also different techniques. But again, the same sort of principles apply. So in this tutorial, we want to perform the finite elements analysis of an I-beam structure using the 3-point bending method. And in order to do that, we'll start by doing the 2D modeling on the CAD side of the solver. Then we'll take it to the pre-post processing side of it, and then perform the finite elements analysis, and of course see the results of the post-processing that we will get of the FEA analysis. So we're gonna start by the I-beam, but in order to simplify the model, we want to study it as a line. So that's one of the techniques of the FEA analysis. You would be able to simplify that. One of the benefits of the simplification, it would be easier if in case you want to compare with your hand calculation, because applying the formula for the line is quite simpler than having a 3D geometry. That's why what we're gonna do, we're gonna consider that one, that's the line, the normal line, then add the force section later on the FEA level, and then bring the a kind of, you know, the condition for it, which basically there are two fixtures on the side, and exactly in the middle there's 500 newtons, and that has been applied. And we're gonna see whether when we're gonna have the bending, and of course as we can predict there should be a bending in the middle, but we're gonna see how the CAE results gonna confirm that. So let's open up the Siemens NX software and see how it performs. So what I'm trying to do, I'm gonna create a new file, click on the new, and make sure I'm into the modeling environment. I'm gonna click on model, and let's call it the I-beam, and let me make sure actually I save it into my local drive. And what I'm gonna do, I'm gonna create a new folder as well. So let me create a new folder. I'm gonna call it the FEA tutorial 2. Open it up, and I'm gonna click on OK, and click on OK. So hopefully you remember from the CAD sessions that how to work with the CAD part of the software. What I'm gonna do, I'm gonna click on a sketch and create a new line in the XY plane. So make sure you're in the XY plane. Gonna create a normal line in here, and with the length of 1500, angle 0. I'm happy with everything. I'm gonna click OK. Let me zoom out and make sure the length is 1500. It's absolutely fine. And what I'm gonna do, I'm gonna click on a finish a sketch, and you can see I just created a normal line, and I'm gonna save it. So I'm gonna click on Ctrl S to save it. And I'm going to open up the pre-post. So I will move from the home to the application. I'm gonna click on the pre-post. If you remember, even I could go from the file and go to the pre-post in here as well. I don't have pre-post because I'm into the pre-post. But again, you can open it up from the here as well. And what I'm gonna do now, I'm gonna click on the new FEM and simulation. This is as you can see here. So by clicking there, I'm going to create two new files, one finite elements modeling and one simulation. It's the I-beam file that I just created. All bodies, yes, I'm gonna have every single things that I have designed, but something is important, and it's I need to go to the geometry option and tell the solver it's the line. I'm gonna just import the line. Because I simplify my model, the I-beam to the line. So I went to the geometry option, click on the line. Solver is by default. I'm gonna go ahead with a Sim Center Nastran. It's a structural analysis. So I don't change anything else. The only change that I done was the geometry option. I take the line. That's it. So what I'm gonna do, I'm gonna click on OK. and I'm gonna let the software to create those two new files for me. Again, in here I'm not going to change anything. I'm gonna keep the SimCenter Nastran as my solver, and also the solution type I'm gonna keep it as the one-on-one linear statics, as well as the global constraint, and everything is by default. I'm gonna click on OK. So as you can see here, this is where I'm working with. If in case you have anything open, you can come here and close them up. So I'm gonna close these so it would be easier for you to make sure where you are. Make sure your simulation file view, which by default usually is hidden, open it up and make sure you have that's your files, the link between the file and the Finite Elements modeling and simulation, the mesh levels and the simulation level. I'm gonna go to the mesh level. And what I'm gonna do, I'm gonna first create the force section. You can either create the mesh and then apply the force section later, or you can start with the force section and then apply the mesh later. I'm gonna start by making the force section first, but then I will then make the mesh later. So in order to do that, I'm gonna go to the more, and because it's just a line, I'm gonna deal with that section, which is the 1D. Now I'm gonna create the force section first. I'm gonna go and click on the 1D element section, and in here I'm gonna click on the create section. By default is on rod, so it depends on what type of the bar you have. You would be able to use a different force section. In this case, I'm gonna use the I, because the I beam, and you have a full control of every single of these dimensions. According to this tutorial, I'm gonna put the 50, 50, and 50 for the first 3 dimensions, and the rest as the 7, 7, and 7. If in case you want to see it, you can click on the preview to see the force section. So it's a 50, 50, 50, and these are 7, 7, 7. And click on OK. And you can see I create the force section. It's the I force section. I'm gonna close this one down. And now what I'm gonna do, I'm gonna create a normal 1D mesh. What I'm gonna do, I'm gonna go to the mesh section, click on the more, go to the 1D mesh in here. Select the line that I have. It's just a one line. The type of it, it's a C-beam. Again, depends on what kind of bar you're studying. It might be different. For instance, it might be a rod. You need to consider the C rod, for instance, the type. These are really important because we are simplifying the actual beam we have. Because the I-beam, I'm going to go with the C-beam type, and then I can pick up the number of elements. Let's say in this case, I'm going to go with 51. Make sure the nodes are merged. So this one is really important. I'm going to merge them together. And also automatic creation is on as well, and I'm gonna click on OK. So if you see here, I have the 1D collectors, and that's my mesh. And if I open this one, you can see that what I've done, created 51 the elements. So now what I'm gonna do, I'm gonna bring that force section that I make, because what I've done, I just created the mesh, but I still haven't applied the core. So what I'm going to do, I'm going to go to the beam collector level, right click on it, click on the edit. Next to that one, I'm going to click on edit again. And in here you can see it automatically asks me for a force section. You can see it's highlighted by this red star. I'm going to click there, and I'm going to pick up the I. That was the name of I-beam. So this is the option I told you. You can actually click there and create a new force section here. What I can do, I'm gonna create a new force section there. But again, because as I already done the create a force section, that would be easier to start with. So that's the I-beam. Let me actually choose the material as well. Let me go ahead and pick up the steel again. I'm gonna click on the steel, make sure it's isotropic. I'm gonna click on OK as well, and OK, as well as OK again. So I apply the force section, but it still is not visualized. I wouldn't be able to see it. In order to visualize it, what I can do, I can go to the beam collector, right click on it, and this time go to edit display, and make sure in here into the beam, I'm gonna go and click on the solid and make sure I tick it. I'm gonna apply, and you can see now I would be able to see the force section. So what I've done, basically still is a line, but now I'm gonna visualize it as the I-beam and study it as an I-beam, but again it still is a line. So it would be quite easier to do a hand calculation and then compare the results together. So I applied the mesh is great, and what I'm gonna do, same as before, I'm gonna go to the simulation level, and I need to start by the constraint type. So I'm gonna click on the constraint type, and these case I'm gonna start with the user-defined constraint. The beauty of a user-defined constraint, you will have a full control of all those degree of freedom. Hopefully if you remember from the assembly, we went through the different degree of freedom, the translation across the X, Y, and Z, and also the rotation across the X, Y, and Z. So what I'm gonna do on the left-hand side, I'm gonna fix the node. So in order to see the node, what I need to do, I need to go to the filter. It's quite important. Make sure go to the filter, click on node, and let me rotate the model. I'm gonna pick up the node that I have. I should only have one node there because it still is one line, right? These things, I don't have any elements there. These are just for visualization. There's one node there. I'm gonna pick that one up, and I'm gonna say, okay, X is free translation across Y and Z are gonna fix it, and also the rotation across X and Y gonna be fixed. So the only thing I have is a translation at X and also rotation at the Z, and I'm gonna click on OK. And you can see I fixed the left hand side. And what I'm gonna do, I'm gonna go to the right hand side and I'm gonna fix it as well. So let me make sure I go to the constraint again one more time. User defined constraint. What I'm gonna do, make sure I activated the node filter, and I'm gonna pick up the node there. And this time I'm gonna fix the first three. What it does is basically there's no movement on the X, Y, and Z, but still they can rotate on the X, Y, and Z. No translation X, Y, and Z, but still they can rotate. I'm gonna click on OK, and you can see that's a representation of it as well. What I'm gonna do now, if you remember, I want to apply the force in the middle. So I'm gonna click on the load type this time. It's the force. So if you remember, there was 51 elements, and I want to apply force exactly in the middle. So what I'm gonna do, I'm gonna find the node 26 and then apply the force there, because it's exactly in the middle of them. So make sure you go to the filter, activate the node again, and once you move these, you would be able to get the numbers of those nodes. So let me see whether I can find the node. Do you see that? This is a node 26. If I move them, nodes 25. So this one, node 26, I'm gonna pick it up there. And the force was 500, if I remember correctly. Let me have a look. That was a 500 newtons. So I'm gonna put 500 newtons. And the vector is gonna be, let me have a look. It's gonna be this one. That one is quite important to make sure. Because we want to put the force on the I side of it, make sure you pick that one correctly, which is the Y axis. So I'm gonna pick up a Y, but it's a negative one. So I'm gonna put it on that side. I'm gonna click on OK. So let me put it to the 3D. Yeah, that's really good. So what we are trying to do, we're gonna apply the force on the I-beam side of it, because the force shouldn't be applied on any part, on the I-beam side of it, which is absolutely correct. And what I'm gonna do, I'm gonna click on actually solve it. But before I solve that, I'm gonna make sure that I have my constraint correctly, my loads correctly, and also they applied on my analysis as well. And now what I'm gonna do, I'm gonna just click on the solve to actually solve my model. So everything seems to be fine. And what I'm gonna do, I'm gonna click on the solve. I don't change anything else. I'm gonna let the software do everything. Gonna let it go. You can see, gonna open up the Nastran. I'm happy with everything. Gonna click. You can see the job has been done. So I can close this one down. The job is completed. So I can cancel this. I can close this one up. And if I click on the result, hopefully the result is going to appear. You can see the structure and it's colorful, which means the structure analysis has been done. I can see the result. I'm gonna double click there and go. Let's have a look on the displacement. You can see, as I was expecting, then it will gonna bend in the middle, and then we'll have a displacements there exactly in the middle. If in case you want to animate it, you can go to animate and click on play to be able to see the animation of it. Let me stop this one. Let me go and do a stress result and see the elemental nodal stress. And of course, you should, as expected, you should have high stress in the middle. You can see the 3.25 megapascal is the amount of the stress you have in the middle. And this is one way of doing it. So what we've done, we try to simplify the I-beam to study it as a line, but in order to let the software is the I-beam, what we've done, although we apply the 1D mesh, because the 1D is a line, is basically we apply the 4 section and studied like that. This is one way of studying the bars, for instance. What we're going to do, we're going to go and continue with one more tutorial. So in this tutorial, what we're going to do, we're going to still study the finite elements analysis of an I-beam, but in this case, the structure is a shallow beam. Still is a 3-point bending method we're going to use, but because it's a shallow beam, we're going to do it a little bit differently and to also experience the other methods of studying these. So what we're going to do, like the previous tutorial, we're going to first make this a structural model and then take it to the pre-post side of the software, perform a finite elements analysis, and then of course apply the solver on it and see the post-processing results. So what we have here, we're going to have a fully symmetrical, the shallow beam, and study one part of it in order to save the computer power and save the time. And these there are fixed on two sides, and then 2000 newtons or 2 kilonewtons force has been inserted exactly in the middle. We are expecting a buckle in the middle, and we think that it's gonna bend in the middle. So let's have a look and see how we can apply these onto the model using the Siemens NX. So like before, let me create a new file and make sure I'm into the modeling environment. I'm gonna call it beam this time. Make sure I save it to the exact folder. So I'm gonna go up, I'm gonna create a new folder. I'm gonna call it the FEA tutorial 3. Click open, click OK. So I save it there. I'm gonna click on OK. And now we are in the modeling environment of the software. I'm going to click on the sketch. I'm happy with the expired plane. I'm going to click on OK. Because we want to make the symmetrical model, if you check the file for the tutorial, it asks you to create a line in between for the length of 50 with the angle of 90. And then what you need to do, you need to right click and convert it to reference and start the model to make sure it's symmetrical. But what I'm gonna do instead, I'm gonna do a Ctrl Z, and if you remember, if I go to the rectangle, if I go from the 2 point and use the 3 points, which basically the first one gonna be the center, I can easily make that model and fully symmetrical without any problem. So I'm gonna do it like that, and the length that I had was 100 and 100 with the angle of the 0, and you can see it become fully symmetrical. What I need to do, I need to make one more rectangle with a 10 millimeter distance. But what I'm gonna do, rather than just draw another one, I'm gonna go here and click on the offset curve, pick up every single of these curves that I have and apply the 10 millimeters distance and get another offset. It would be quite easier in order to draw one more rectangle. So I'm happy with everything. I'm gonna click on the finish sketch, and what I'm gonna do, I'm gonna extrude it for the 1500. But if I extrude it like that for 1500, it won't be, so it becomes like that, it won't become symmetrical. What I'm gonna do, I'm gonna extrude symmetrical on both directions. So I'm gonna extrude it for 750 on each side, and that would enables me to, once I'm gonna study it later, you can find out what's the reason I'm gonna use this method to have a fully symmetrical, and I'm gonna have a plane in the middle. That would help me a lot on the other part. I'm gonna click on OK. So once you're happy with everything, make sure you click on Ctrl S or save it. And now I'm going to the application and click on pre-post. As I mentioned, I can also go to the file and click on the pre-post. It's the same thing, doesn't matter. And in here, you can see I have an option for a split body. The reason we're gonna use a split body, assume that this model has or needs lots of the computer power in order to do an analysis on it. And because this model is fully symmetrical, what I'm going to do, I'm gonna only study one part of it, half of it, and lets the computer duplicate the result for both sides. This would enable me to save lots of time. It's the same thing for lots of the calculation as well. So this method we will use it on the for symmetrical models, for instance. So what I'm gonna do, I'm gonna click on the split bodies, and I'm gonna pick up the body that I want to make it into the half. I'm gonna click there, and now I have to specify the plane that I want to split it in two. The reason I've extruded in two directions symmetrically, because I have that plane exactly in the middle. I can click on OK, and you can see I have my model has been splitted. So what I'm gonna do now, I'm gonna go to the new FEM and simulation, and you can see two files now is going to be created, one finite element modeling and one simulation. It still is a BIM file that I have, but this time I need to decide which body I want to import, because if I put all visible, what it does, it import both, and I want to import just one of it. So let's import this one. So you can see this split it from there. And again, geometry option, I'm gonna keep everything default. I don't want to specify any other things, because basically I'm gonna bring and import the full model, just that part of it. The solver, again, I gotta go with a sim center Nastran. It's a structural analysis, so I don't change anything. The only thing what I've done, I split it in half and I imported one body. So I'm gonna click on OK. And in this also page for the solver, what it shows, I don't change anything. Still is a sim center Nastran solver. The analysis type is structural. Also is a linear statics and global constraint. I don't change anything else, and I'm gonna click on OK. And you can see just half of the file has been imported. So what I'm gonna do, let me close this one for the previous model, so we know that what file we are working. Again, it has different levels: the part level, the mesh level, and a simulation level. While I'm to the mesh level, I'm gonna apply the mesh, because the 3D model, I'm gonna apply the 3D tetrahedral, which is quite common. In terms of the body, is basically this body that I want to import, and I'm gonna go with a C tetra type, which basically has the 10 nodes. So the C tetra 4 has 4, 10 has 10 nodes, and the element size, I'm gonna go. Let's first to see what software recommend. It recommends 45.3. I think it's too much, to be honest. Let's go and change it to 25. I need much more number of elements, so I'm gonna change the element size to 25, and make sure I increase the local machine each for 50%, so both on to the inner part as well as the internal part by 50%, and I'm gonna click on OK. I let the software to discretize and mesh my model. So now if I go to my beam, and you can see 3D collector, because there are 3D meshes, they put them in 3D. These are solid meshes. And let me open this one up, and you end up by 3,999 number of elements. So what I'm gonna do now, I want to apply the material. So I'm gonna right click on the solid, go to edit. Let's click on here. Let me go and click on material, and let's choose a steel again. It's isotropic. I'm gonna click OK. Gonna click OK. So by applying the material, basically I'm gonna give the material property to the solver, so you can understand the material characteristics once you insert the forces. And now everything has been done on the mesh level. I'm gonna go with the simulation level, and now I'm gonna apply the constraint. So I'm gonna apply the constraint on that side first, and so I'm gonna go with the user defined constraint. Let me bring this one here. I'm gonna apply it on that side. So make sure it's the correct side. This is not the because we make it half in there, and you can see it from the coordination system. So I'm gonna apply the constraint here. Make sure, if in case you're, because I think from the last tutorial we applied the filter is on nodes. Make sure you go back, because I'm gonna pick all the side in here. I'm gonna pick up the face, so I don't use any filter this time. And degree of freedom, however, in here, the first two are fixed according to the tutorial, as well as the last two. And what it means, no translation at X, no translation at at Y, but you have translation as Z and you have rotation at X. I'm gonna click OK. Because we split the model in half, basically the kind of constraint that I have there, also I have it on the other part, which I don't see it. So what I'm gonna do, because I'm gonna let the software that this model is fully symmetrical and I have the constraint on there which I cannot see it, I'm gonna go to the constraint type and pick up the let me have a look in here, a symmetric constraint. A symmetric constraint, what it means is basically copy the constraint you have on the other parts of the model as well. And I'm gonna say the model is being halved exactly in the middle, so the constraint onto the other part is the same as the constraint that I have there, and that's why I use this symmetric constraint. So what I'm gonna do now as well, I'm gonna apply the force exactly in the middle. So I'm gonna go to the load, click on the force. It's a normal force. I'm gonna pick up this plane. Make sure, if in case your node has been activated, go to the filter, change it to the no. I'm gonna apply a force here. The amount that we have according to tutor was 2000 newtons, and make sure I correct the which one it is. It's a y-axis. It's the x-axis according to the tutorial, but again I want it to the opposite direction, so it's this one. I'm gonna click OK. So what you can see here, this model has been fixed there, and also we inserted force on that side. And what I'm gonna do now, I'm gonna click on solve and let the software apply the solution for it and solve it for me. Because this model is quite simple to bend, it doesn't take time. But of course, if you have a complex model, once you apply the split bodies, you can see that how much time you can save, how much time and resources, because you need to have access to the much more powerful computers. So I'm gonna click on yes. This one is finished. You can see it's completed. I'm gonna click on cancel and cancel. And now I'm gonna go to result. You can see the structure now is up here. I'm gonna double click there. And let's have a look on the displacement first, the magnitude of it. Of course, I have much more displacement because you are inserting the force, and you need to assume that your model is like that, because the rest you don't see it here because we just study one part of it. And if you want, I can animate it as well. Let's have a look. You can see that once I insert the force there, I need to because it's trying to bend in the middle, and it's basically you have much more displacement there, and the maximum displacement is a 0.16 millimeter. Let's have a look on the, for instance, the stress. Let me go to the stress elemental nodal, and if I click on von Mises and let me stop the animation, you can see that I have 12.81 megapascal stress on the middle as well, and this is what I'm exactly looking for. Even if you want, I can make it as a band that you can see that this area is the area that I have the much more stress. If I want to read it like the first one, I can go and get the results from there. Basically, let me have a look. You would be able to see that I have 12.43, for instance, on the megapascal stress that I have on there as well. If in case you want to get the graph, you can click there. So this is it, and you can see it become much more faster because what I've done, I split the body into the half in order to need less computer resource, to be honest, and save time. It would be quite easier for the calculation as well, and that's why we split it to the half once you have the symmetrical model. Let me save it, and now if I go to the file, you can see that in here for the tutorial 3, I started with the beam file, and these are all the finite elements modeling and simulation and the rest of it. So it's really important you save it in one folder to be able to save all in one. So whenever I move this file around, I still have all those kind of connection with each other, and I don't lose anything else. So that was basically for the introduction to finite elements modeling and analysis using the Siemens NX. I just touched the surface of the FEA. It's a really important and a big topic, but within an hour and a half, I just wanted to briefly go through it, hopefully give you a good sort of idea if in case you want to run the finite elements analysis using the Siemens NX for your project or for your assignments. I think this gives you a good understanding of the software environment and how it works, and also the stages. So we always start from the part level, and then we take it to the next level using the pre-post, and then we discretize the model, we apply the mesh on it, apply the material, then we go and apply the constraints basically in order to make the environment, and then I apply the forces. And that's it among any other softwares, to be honest. But this is how it works in the Siemens NX. If in case you have a different part or a complex part, the kind of constraint will change, the kind of forces will change, but the rest is almost the same as what it is. So that's why these, I think, will give you a really good idea, but the rest, of course, you need to spend much more time at your own to experience these and practice these. Thank you so much. If in case you have a question, please keep in touch with me, and I will see you into the next drop-in session. Take care and enjoy your time.